Hello everyone, thanks for joining me. Today I'm going to talk about our paper from CVPR called Similarity Maps for Self-Training with Supervised Rate Rounding. This paper done under the supervision of Professor Leo Wolf in Tel Aviv University. And in this paper, we're utilizing the state-of-the-art algorithm for phrase rounding, and we refine the output mask by generating similarity maps between the features, the special features in the lattice space. And by aggregate those maps, we get a pseudo label that are more accurate than the initial output of the first grounding. And by fine-tune this model, we achieve better performances. So let's take a look on how we do that. So in the current state of the art architecture for phase grounding, we use two encoders, one for visual inputs for the image, and the second is the text encoder for clip. We calculate the similarity between the text features and the spatial features of the image, and we get a similarity map, ZG, and by product with these features with the lattice space, we achieve weighted lattice space given the text, and we generate with the decoder the output mask. In our solution, we utilize two encoders with G checkpoint, and we know that the visual features are aligned with the text, and so the spatial features can be indicate for semantic similar for objects, and therefore we calculate the vectors similarity with each other, and we got a map that for each vector that we need to aggregate and to think we use them in order to obtain the shape of the objects. In this slide, you can see examples for similarity maps. So the green dots are related to an object with a semantic meaning, with the same semantic meaning, and the red and the blue dots are related to another objects in the image, and B and C are related to the similarity maps of the green dots, and D and E are related to the red and the blue dots. And we can see that our assumption are correct, are getting proved here by this visualization. So now let's look how the pipeline works. So we get an image and we use a G network, which is the state of the art of phrase grounding, and we generate an output map that related to the text. Here we can see a Japanese woman, and we get the pixels that are related. We can see that these examples are not so accurate for G, and we generate relevance maps, which is the similarity maps that have overlapping above a threshold with the output map of G, and we call it a relevance map. And from those relevance map, we average all the K relevance and to obtain a pseudo label, which are more accurate. With this heuristic, we improve the performances with G without any fine-tuning. Here we can see another example, and here we can see another example. But only improve the performances with heuristic is not enough, and we thought that maybe fine-tuning G will obtain a better results, an accurate map. And how we do that? So we call M bar the pseudo label from G, and with this pseudo label, we train G++, we call it, with the previous losses of the WWBL architecture, with one exception. We replace the extendability map of clip with mbar. So the pseudo label, we call this loss, is just L2. So the output map of G++ need to follow the mbar. And we also add the foreground and the background loss and the regularization from the previous paper. So we can see visualization for this fine-tune, where we have a text, we have the input image with the ground truth, and we have the output of the original G. And the last column is G++ output. You can see that we get fine maps and more accurate maps that capture the oval shape of the objects. And here you can see some numerical results for phrase grounding and WWBL tests. You can see that we improved the performances with a large gap comparing to the previous state-of-the-art WWBL, and which represent by G. And we also did an ondulation study where the first row is only the heuristic without the fine-tuning. So here we can see that the fine-tune is also improve the performances compared to the heuristic. And we also examine the impact for each loss term. And we can see that we need the all terms in order to improve the performances and achieve the state-of-the-art performances. And we also replace G with a segmentation encoder, which train on closed sets of categories and with supervision. And we use a classification encoder, VGG, which only train on image labels. And we can see that our model are much better with our encoder from the phrase counting. So thank you very much for listening to our presentation. And if you have further questions, feel free to connect us. Here we can see a QR code for the paper and the code. So thank you very much and hope to see you in the conference.